In this presentation, we're going to look at how to compute confidence intervals. Okay, the matter of what confidence intervals are and are not are important, but not the key thing for this presentation. So, confidence limits are the upper and lower boundaries or values of confidence interval, and that's to say the values which define the range of the confidence interval. So this is very important. This is, let's get the proper font there. This is the general structure of almost all confidence intervals. The point estimate, which would be the sample mean or sample standard deviation or the sample proportion or whatever, plus or minus the quantile. Now that's a quantile from some probability distribution, mostly the t distribution, okay, times the standard error, okay, and that's related. That standard error is like essentially the standard deviation of the sampling distribution. That's quite important. But in a nutshell, if you're looking at all various different types of confidence intervals, they follow this general structure very closely, okay? So point estimate for population parameter of interest, so it could be sample mean or sample proportion. Quantile, a value from the probability distribution that scales the interval according to some specified confidence interval, okay? Quite important. And standard error measures the dispersion of the sampling distribution for a given sample size, n, okay? The sample size here is of particular importance, okay? So n, I'll just put it in there. N is quite important. Okay. So, let's move on. The little bit of revision here now. I'm just going to go down to the next slide. A 95% confidence interval. So essentially, just as a sort of important remark, you might sort of specify that, like a confidence interval, you might specify a certain confidence level, and usually you will work with 95%. Confidence interval, 95% confidence interval, is a range of values which contains the true population parameter, mean or proportion, with a probability of 95%. And we can expect that a 95% confidence interval will not include the true parameter values 5% of the time. This is a sort of corollary to that statement there. It's essentially what the definition is of a confidence interval. Essentially, you mostly in undergraduate statistics, you usually you would use 95%. But depending on what sort of subject area you get into later on, you might go as low as 90%, like for business applications, or 99.9% for what that would be sort of medical applications. It depends on how confident you really need to be. Okay, so the next thing we're going to look at is, let's go down here. Oh yeah, so some of the notation here. This is quite important. I'll just go scroll down here a bit more. A confidence interval for is oh, there we go. Sorry, it's just this is a bit jumpy when all the software is running at once. A confidence interval for an interval is denoted to 1 minus alpha. That's alpha there. Okay. Or in terms of a percentage, you might write it like that: 100 times 1 minus alpha for some value alpha. Alpha, if we're talking about 95%, alpha is 0.05. Okay, so a confidence level of 95% corresponds to an alpha of 0.05. And there you go. There's a little sort of way how it works out. Okay, that's that line there. This one here, just sort of let you look at that yourself. Just try that with a bit of pen and paper. So for a confidence level of 99%, you would sort of say that alpha is 0.01. Now, knowing the correct value for alpha is quite important in determining quantiles, because they are how you would sort of pick out your quantile. Just as a remark, I've not actually formally introduced it yet, but if you recognize this as the thing called significance level, then you're not wrong. Okay, it's not that I'm not actually introducing it yet, but it is. You are correct if you think that's related to the significance level. It's not brought into play yet. Okay, but there's something later on, if you're not seeing it yet, called significance, which is quite important. Now, let's move on. Quantiles. The quantile is a value from the probability distribution. Now, oh, there we go. So the probability distribution is For large samples, usually what you would use is the normal distribution. Okay. And for small samples, you would use a distribution called student t. Now they're very similar. And it scales the interval according to some specified confidence level. So if you want your confidence level of, let's say, 95%, you have to pick out the right quantile that will give you that. Now, for practical purposes, the quantile can be taken from the standard normal distribution. If you're not familiar with that, that's the Z distribution. Okay. If the sample is larger than 30, further to the central limit theorem. Okay. So essentially, if it's large enough and the sample size is greater than 30, then you just you can sort of base your answer on the standard normal distribution, or the Z distribution, or Z distribution. Just as a remark, sometimes this is actually given as 50, and the reason for that is actually the way that tables are printed. Sometimes they're written with 30 rows, sometimes they're written with 50 rows, and it's just whatever level of accuracy is offered in the student t distribution. So essentially, if it's too big for whatever's printed, they just use the standard normal. It comes to the point where the differences are negligible. Okay, so for a specified confidence level of 1 minus alpha, the corresponding quantile is the value z0 that satisfies the following identity. Okay, where an n is greater than 30, greater than or equal to 30 actually. Well, no, greater than 30. So, for example, I'll just give you one that you would sort of commonly use. Now, this is actually related to the normal probability distribution. So if you were to check this with the normal probability distribution, you'll find that you would get an answer of 0.95. Okay? And so on. So that would correspond to a significance level of 5%, or a confidence level of 0.95. Okay. Now, when the sample size is larger than 30, we can compute the quantile using the Murdoch-Barnes table tree. This is what I would use for my course. Okay, and that's just the other example that I've given there. The 95% is the quantile for 2.5%, is 1.96. That's the quantile for 2.5%. That's to say, for the Z distribution, 2.5% of the values are less than 1.96, and the upper bound is plus 1.96. So I just paused there just to sort of get my slides back on track. So when the sample size is greater than 30, we can compute the Murdoch-Barnes table 3, and okay, just as I sort of said there, 2.5% or 2.5% are less than 1.96, and 97.5% are less than 1.96, and the difference there is 97.5% minus 2.5% gives you, the difference there would be the 95%, so it's a symmetric interval. Okay. Similarly, so that's the quantile that you usually use for a 95% distribution, or 95% confidence interval. If you were dealing with a 90% confidence interval, okay, you would use 1.645, okay, and a 99% one you would use 2.576. Okay, so now that's the important parts. Now what I'm going to do is actually talk about the next part here, is the 3 different types of confidence interval for a sample mean. Okay, first off, sample mean confidence interval, we have 3 different types. So first off, we have a type 1. I'm going to call it type 1, type 2, type 3. Type 1 is known population variance. Okay, and the size of the sample doesn't matter. It's the one we'll just sort of start off with. It's not usually the most practical. Either 2 or 3 usually are what you would encounter in practice, but type 1 is what is, you'd use it to sort of ease yourself into it. Just the whole matter of confidence intervals. The second one is type 2, large sample with unknown population variance, and it's a large sample with more than 30, and a small sample with an unknown population variance, and it is 30 or less. Okay, so let's go down here. So the first one, known population variance. Okay, plus or minus the quantile. So that's the quantile there. Okay. And essentially you just pick out one of the two values. If you have plus or minus 1.96, that would be the exact same as plus or minus 1.96. Okay, so it doesn't really matter which one you pick. Quantile, because you'll actually, if you sort of apply plus and minus to both, the answers will work out the same. Okay, the plus and minus operation. This type of confidence interval is very rare in practice, but it's very simple to implement and use in introductory teaching material. Okay, so essentially what we have here is our sample mean, x bar, okay, our quantile from the distribution, and then the standard deviation divided by the square root of the sample size. Okay, so the standard deviation is sigma and the sample size is n, so we get the square root of n. Okay, so the point estimate there is x bar. We use the quantile from the standard normal z distribution to scale the confidence interval to the specified, okay, 95%. So in this case, what would happen there is we will go for a 95% confidence interval. Essentially what we'll do is try and get our probability distribution, or a quantile, such that it gives a value in excess of that, of this value here. This is really important here. Okay, alpha over 2. That is to say 0.5 over 2, or in other words 0.0250. I'll just write 4 decimal places. Okay, why are we using that value? That's really, really important. And I'll tell you what I'm going to do here is just realize I've gone up to 12 minutes now, as I'm going to stop there and start a new presentation. So this is Computing Confidence Intervals Part 1. I'm going to leave it there on the cliffhanger, and then we'll go on to the next one.